Hey everyone, my name's Matt. Today I'll talk a little bit about some of the work that I've been doing searching for parity violation in the galaxy distribution with deep learning. So the first question is, why are we using deep learning for this task? Well, a lot of previous work that searches for parity violation in the galaxy distribution uses the 4-point correlation function. And so some examples of these papers that I've listed here. And one of the difficulties that we find a lot with this sort of approach is that there's a heavy dependence on the choice of mock you use. So effectively with this approach, you need to sort of do some calibration for the 4-point. And to do that calibration, you need some mock simulations. And if they don't match your data exactly, then you can start to run into some issues. So the thing that we want is an alternative that doesn't require these mock simulations. And that is what detecting parity violation with deep learning lets us do. So the approach that we go with is we start with the whole universe, or at least some survey of the universe, some observations that we've got, and we split that up into little patches. And for each patch, which I'm calling X here, we apply a parity operation, which effectively we flip that patch and we look at its mirror image. And this gives us a set of patches that belong to the mirror universe. So this is sort of one way of thinking of what we're doing. And the idea is that we feed into our machine learning model our universe and the mirror universe, and it will somehow learn the differences between those and be able to distinguish if a patch comes from our universe or the mirror universe. And this is actually kind of all you need to tell that there is parity violation. If you can effectively distinguish between if something belongs to our universe or our universe with a parity operation applied, then you are effectively detecting some sort of parity violation. So at the end of the day, what we want is a machine learning model that we can feed in a patch from the real universe and it'll say, yes, that's real, or likewise for the mirror universe. But this sort of classification doesn't really help us with science. Instead, it's a little bit better to work with a continuous output. So in this case, the real universe might give us some sort of high value like 1.02, and the mirror universe might give us a low value like -1. So for a little bit more of a formal approach, if we assign our patches to be called X and our mirror patches to be called PX, then what we're doing is we're building a machine learning model, which is just a general model at this stage called G, and we want to apply that to X and PX, and we want to maximize the difference between these two. The difference here I'm calling f of X. So once we compute that, f of X is the parity violation statistic, basically, computed over one patch. And throughout training, what our goal is going to be is to maximize the difference for the model applied to each of those. And that way it will be able to effectively distinguish them because high values will be from the real universe and low values will be from the mirror universe. So one really important question here is, how can we make a statistically rigorous detection? Just because we have a model that can tell the difference in our particular sample of data doesn't necessarily mean that we've actually sort of discovered interesting new physics. And so this is kind of one of the most crucial parts of this approach, is making sure that we can really make a claim that what the machine learning model has learned is a statistically rigorous detection of parity violation. So the way we go about doing this, firstly, is we take the average of the f of X computed across all of the patches in the data, or at least all of the patches in an unseen validation portion of the data. So the model will train on part of the data, and then the other part of the data where it's never seen before, it needs to prove that it's still detecting parity violation. So we compute f of X over all of that, and we take the mean, and this is our mu value. And if mu is greater than 0, then that's a good indication that there is parity violation in that validation set. But the question is mu greater than 0 because of an actual parity violation, or is this due to some sort of natural variation in mu? had we done our survey in a different spot in the universe, would we have actually seen a low value of mu that would sort of balance out the high value we see in our real data, for example? So it's very important to figure out if what we're looking at is truly an indication of parity violation. So what we can ask is, how would mu vary if we could observe many such surveys? So for example, if we looked at our survey and data, we might see that we get mu is equal to 2.1. If we could, magically observe the same thing again at a different part of the universe, maybe we'll see that mu is 1.9, and then again 2.0, 2.1, and we can start to build up a distribution of how mu varies across all these sort of many surveys. And if this distribution is very, very different to the value of mu equals 0, then we can basically exclude that the parity violation is caused just by a random chance. And we can be sort of certain that this is actually coming from true parity violation. But unfortunately, we don't have many surveys. We only have one survey. So we need to come up with another way of doing this. And the answer that we've come up with is computing the bootstrap distribution of mu for just one survey. And you'll see in this plot here, this is a distribution of, in the shaded region is when we take the mu value over 10,000 full surveys. And this is for some mock data that I will show a little bit later. But for now, that's 10,000 full surveys. And you'll see that's sort of the distribution it takes. It sits around 2.1-ish. In the line here shows 10,000 bootstraps of a single survey. And you can see that the variability in the distribution matches very, very well. So it's actually, the bootstrapping gives a great estimate of the true variability of mu that we would recover if we were able to take 10,000 actual full surveys, even though that's not something we could feasibly do. So the fact that we can sort of capture this variability with just the bootstrapping process is great news. And the reason this works so well is because in creating our parity statistic, we have a compression of the field that's very, very highly compressed. It's just a single number that represents all of the parity information in that field, which lets us use this bootstrapping process. You'll also notice that the bootstrapping is slightly shifted off. The reason for that is because the bootstraps will have a mean about the true mean in that single one survey that they've been bootstrapped on. So in this particular example, the true mean of the one survey is slightly lower than the overall mean of our 10,000 surveys. So that's why there's this little bit of a shift. The shift itself is not important. What's crucial is that the variability matches. So then how confident are we in this detection? How can we sort of assign a number to how confident we are that the true mean of the universes, or of the universe, of all of these surveys of the universe, will come out to be greater than 0? And the way we can do that is by taking the sigma level of detection, which we've defined as the mean of the bootstrap distribution divided by the standard deviation of the bootstrap distribution. And so effectively what you're doing by taking this is counting out how many standard deviations, you can see in the blue here, how many standard deviations away from 0 the mean of this distribution is. And so that is basically our threshold. If it's more than 3 standard deviations, then we can safely say that the overall mean, had we had access to all of these samples of the universe, would in fact be greater than 0. And we can be statistically confident in that claim. So now onto the deep learning model. The actual specific deep learning model we use involves 2 steps. We isolate those. The first step is data compression, which takes the entire input field and crunches that down into a set of summary statistics. And then we pass that set of summary statistics into a fully connected network that then condenses that down further into a single number. And the reason we separate this into two steps is because the data compression process here is really, really important, because this is, if we add basically too much flexibility in here, we don't have a lot of data to train our model. So adding too much flexibility means that you can get all sorts of overtraining happening, and basically you get a model that doesn't extend well to any unseen data. It's just learnt the parity violation in its own specific data set. So by separating out the data compression step, we can actually use some non-machine learning or like very loosely deep learning approaches in that compression step, and then pass those through to a fully connected network. And keeping those separate can make things work out a little better for us. So the types of compression model that we've investigated so far, firstly, convolutional neural networks. So these are super flexible. These are sort of your standard go-to for understanding image information. These are potentially too flexible for our case because we just don't have enough data in a real survey to train them in any successful way. And we certainly find they tend to fail in 3D because they just end up memorizing your data instead of learning useful correlations. So an alternative is the Wavelet Scattering Transform in the middle. And WSTs are basically like an untrainable version of a CNN. They have fixed convolution filters, and this makes them very robust, and they utilize a lot of symmetries that match our data, and they're very, very good at extracting cosmology information. In fact, a lot of other work has found that. But in this particular case, they're not flexible enough because the filters themselves, by default, aren't actually sensitive to parity information, or are very lightly sensitive to parity information. So it turns out that these aren't really the best approach for us. We've also tried graph neural networks. This is more work that Carol's been doing, but these have worked brilliantly in 2D, and we're currently developing the 3D version. So we'll see how that pathway goes as well. And the compression model that I've used the most is the neural field scattering transform. So this is a model that I've been developing where effectively you take the filters that normally occur in the Wavelet Scattering Transform and you allow those to be trainable. And they're trainable in the form of what's called a neural field. Basically, this just means you have a set of flexible filters that can better adapt to the task at hand. But because you've maintained the Wavelet Scattering Transform architecture, what this means is that you end up getting a robust statistic that can extrapolate quite well, even given limited data. And so we find that this does in fact work in 3D. The asterisk is there because it could definitely work better. We're still trying to really figure out the best way to implement this such that we will get a good, strong, rigorous detection of parity violation. So I'll just quickly go through a few proof of concept results. So at the moment, we've been using relatively simplified data. On the left here, you can see two triangles. These are L-shaped triangles in a sort of imaginary field of data. I've indicated in red and blue which the two triangles are, and you can really clearly see that these are L shapes, right? If you flipped this, you would no longer have L shapes, you would have reverse L shapes. So this would be a parity violating shape, or a parity violating distribution of galaxies. When you start to increase that, so the one on the right here is 16 triangles, suddenly you can't look at that by eye and go, yeah, that's a bunch of L's, that's parity violating. It just looks like a random distribution of points. So ideally, our model will be able to pick out that this distribution on the right is in fact parity violating. And that is exactly what we see we can do successfully. So in this plot, I have the NFST, the WST, the Wavelet Scattering Transform, and a convolutional neural network model. On the x-axis, we have the training dataset size, which is effectively just how many training samples it sees, how many of these patches that it sees over the training process. And on the y-axis, I have the sigma level of detection, how confident we are that it has actually detected parity violation. And you can see that the NFST in red outperforms the other models by a significant margin at all training dataset sizes. You'll notice that the WST doesn't really do very well. I should say the dashed black line is the 3 sigma detection threshold. So if it's above that line, that means we say it has successfully detected the parity violation. So the WST sort of sits around that line, but doesn't really push past it very much. And this is because the WST is not naturally sensitive to this parity violation, or it's not very sensitive at least. You'll see the CNN gets better and better as we introduce more data, as does the NFST, but slightly less respective to the CNN. But this is because our NFST is nice and robust, and it works particularly well down at these small training dataset sizes. So if I zoom in a little bit, down to just 50 training patches, you can see that the NFST does make a detection, which is a really good sign that this model we've come up with is able to detect parity violation even with few data samples. So I'll just quickly go through some of the benefits of deep learning. Firstly, and number one, is that no mock simulations are required. Because we've got such a strong compression of the field, we anticipate that we'll be able to make this detection without requiring any simulations as a sort of calibration, which is ideally exactly what we want. We don't want to have to rely on any assumptions that come with our simulations having to match the real data. So this part's really good. It's also very flexible. We're effectively discovering a new summary statistic that can take any information in the field, however higher order it needs to be, depending on how we set up our compression model. But basically, you can access 4-point, 8-point, whatever you want to capture that information. It's also can be quite informative. There's a big thing about machine learning being quite sort of a black box where you can't interpret how it works or what's going on under the hood. This sort of applies, but a lot of the compression models that we're trying to use, you can actually directly interpret the scales and sort of what information the model is accessing from the inputs to make its decisions. So there are ways we can get around this. It's not perfect, and it's not going to be as clear as potentially using something like a 4-point, but there are definitely ways that we can start to look into that. And this is a field of machine learning that is developing very rapidly because a lot of people want to understand how these models are working under the hood. And I'll make also the claim that there are no false detections. So if we have a sigma level of detection that's greater than 3, then we can say, yep, we've got a 99.7% chance that we have made a detection of parity violation. There's a very big asterisk here that just because we have a detection doesn't mean that there is actually a parity violation in the physics. It means that there is a parity violation, but it could also be from systematics in the survey. And this is a common problem amongst most ways of searching for parity violation is you've also got to worry about the systematics. So in the future, our goals are basically extend to 3D, get it working in parity violating simulations. So these are, for example, the Quixote simulations have a parity violating suite. So they're sort of our golden standard. If we can get it working on that, then we'll be very happy. And then finally, apply to the real universe and see if we find parity violation or not. So as a quick summary, deep learning can be used to search for parity violation in the galaxy distribution. It's a really, really flexible approach, and it doesn't require mock simulations, which is a big plus. And keep your eyes peeled for the 3D application soon. And I'll just also plug, we've got 2 papers out. The first one uses a CNN model, and the second one uses my new NFST model. So thanks very much for listening, and have fun at the rest of the conference.